Hi, I'm going to talk about active learning. That's the topic I chose for the assignment. While making this video, in fact, while learning about the topic myself, I referred to Burr Settle's video lecture, and also to Sanjay Dasgupta's video lecture. They helped me a lot to learn more about this topic, about this field. Please sit back and enjoy. I hope you like the video. First, I would like to talk about the motivation behind active learning. Now, in this era of big data where everybody has access to the internet, it is very easy to get data, whether it is documents or images, is just a click away. However, all this data is unlabeled and it is very expensive to get somebody, a human being, to sit at the computer and label or annotate this data for you. And that is where active learning comes in. Because all this unlabeled data, which is, as I said, expensive to get labeled, in fact, not just by human beings, but also at times it's expensive to carry out certain experiments that assign a label to it. Like, let's say if it's a drug trial, assigning a label to a tested drug, whether it's good or bad, would require you to make somebody have it, and that's not always possible. So now or probably you don't want to do it as much for all the data points that you have. So the solution, of course, is active learning. Now the idea here is that our learner should be able to query the oracle. The oracle here being the human being sitting at the computer annotating the data. So our learner should be able to query the oracle only for a few instances, not all of them. Unlike now this is very different from the traditional passive learning settings. Here the learner actively queries the oracle for instances it's most uncertain about, or the instances it feels are the more relevant. It then retrains the classifier using these newly obtained labels, and this process keeps on going. That is what active learning is. Now let me just give you probably a easier visual explanation. Now if you look at this distribution here, you can see that there are multiple decision boundaries that are possible when I don't take the unlabeled data into account. Now if you move on to the second image here, you see that all these orange blobs are the unlabeled data, and when I take these into account, you can probably see those two clusters emerging. All I want to say here is that like probably drive home the fact that taking unlabeled data into account gives you more information, and that is what active learning is trying to do here. It in fact gets better results because it is taking into account those unlabeled data that those were previously ignored by the supervised learning algorithms. Now there are three query scenarios or settings that we have. First is the query synthesis, selective sampling, and then we have the pool-based active learning. I'm going to talk briefly about each one of them. Now the query synthesis is the ideal scenario. Here you know the underlying natural distribution from which all the points are being drawn. You generate a very good informative instance xi, and then you query the oracle for this instance, get its label, add it to the training set, and then retrain your learner. However, this is not really possible because for this you need to know the actual underlying natural distribution, which you do not always know. So then comes in the two other practical methods, first being the selective sampling. Here you have a continuous data stream that's coming in. You get to observe only one instance at a time. When you observe an instance, you decide on the spot whether to ignore it or whether to query the oracle for its label. How you decide that is on the basis of some heuristics which we're going to see in the consecutive slides. But then for now, let's just say that if you think that the point is not informative enough, you're going to ignore it. But then if you think that it's a point that's going to help you better your classifier, then you're going to query the oracle for its label. Now, what are these relevant instances? So again, I wanted to give you a visual intuition. Here, if you look at this this distribution, so I can say, looking at this orange blob here, that most probably it's going to be a positive instance. It's in between all the other positive instances. So if I query the oracle for this instance, this unlabeled data, it's not going to be very informative because I already kind of know that it's positive. It's not going to it's not going to change my decision boundary in any way. However, these points here, which are very close to the decision boundary, and even this one, which is an outlier, are probably going to affect my decision boundary and will make my classifier better. So it makes sense to query for these points. So this is the notion of the relevant instances, or the informative instances, or the instances that the classifier is not really sure about whether it's going to be a positive or a negative. Then it queries the oracle for it. That's the intuition here. Okay, now how do you go about selecting the queries? That's the next question. The most common, or the first thing probably that comes to your mind, would be random sampling. I'm going to randomly go about, pick out some points, unlabeled instances, ask the oracle to label them, and then add them to my training data set, and then retrain my classifier with those and keep on doing that. However, that does not work, only if life was that simple, right? That doesn't work because you'll see that gradually, after a while, the training set that you get, the training set that you're building up, will look nothing like the underlying distribution. This happens because of the sampling bias. In fact, this is one of the biggest problems in active learning that you continuously try to defeat. So instead of random sampling, what we do is called uncertainty sampling. We sample, or we query the oracle for only those points which we are the most uncertain about. And that makes sense, right? When you cannot decide what is going to be the label, you ask a human annotator or the oracle for its label. Otherwise, you don't bother. Now, how do you decide whether a point is informative or relevant, or that you're uncertain about it? Well, there are various measures like that you can minimize the least confident objective, the smallest margin, or the entropy. These are the algorithms. So this is how your pool-based active learning then gets modified. How you would proceed is that you would evaluate each instance xi in the pool, rank and query the top k instances, and then retrain and repeat. In selective sampling, you will threshold a region of uncertainty. Then when you observe new instances, you query only those that fall within this region, and then you again retrain and repeat. However, uncertainty sampling doesn't always work. That is because we're using only one classifier here. So the solution that was thought of was that, how about we use two classifiers called G and S, which lie into extremes of the version space, and the learner then queries an instance only if these two extreme classifiers don't agree on that instance. Only then. If they do agree, good enough, then I do not need to query for the point. But then if they don't agree, I query for the point. Now, before going further, I would like you to look at the vague distinction in active learning. There are two types of active learning algorithms. One is the aggressive and the other is the mellow algorithm. The aggressive algorithm looks at the most informative point. It wants the most informative point, while mellow active learning algorithm simply avoids redundancy. Now let us look at the query by committee algorithm, which is an aggressive separable data case. Here how we talked about the G and S classifiers, the extreme classifiers. Here we do not have those specific G and S classifiers, but we have a committee of classifiers. That's the only distinction. So here we train a committee of classifiers C. Whenever we observe new instances, we only query those instances for which there is a disagreement in the classifiers, then we retrain and repeat. For a pool-based active learning, you train a committee, you measure disagreement for each instance xi in the pool for each one of those committees and each one of those classifiers in the committee. Then you rank and query the top key instances and then retrain and repeat. Now let's talk about the generic mellow learner. I would talk about this in more detail. Let's define the setting again. The setting is similar to the selective sampling setting. Let me define that again. Here you have data points streaming in, and each time you see a data point, you have to make a spot decision whether or not to ask for its label. All these points are IID taken from an underlying distribution. Now here we maintain a set of candidate hypotheses. Now what happens when a point comes in? So when a point comes in, we look at all our candidate hypotheses. If they all see it as a 1, good enough. I do not do anything. I do not query for that point. Similarly, if all the hypotheses agree that it is its label is a 0, again we don't do anything. However, if there is the slightest disagreement, that is, even if one hypothesis differs, then we query the oracle for the label of the point, which makes sense, right? Again, it's intuitive. We now add the new hypothesis to our pool of existing candidate hypotheses. So here we see that how the mellow learner only avoids redundancy. This figure here shows you the region of uncertainty. This yellow region here is the region of uncertainty. It's the region from which the classifier picks the unlabeled data points to be queried, or whose labels it wants to know from the oracle. Now there are two big issues which are pretty obvious actually here with the mellow learning method. The first is that this set of candidate hypotheses that you have to maintain, explicitly maintaining them is intractable. So instead what you do is that you implicitly maintain them using supervised learning. So whenever you receive a data point, an unlabeled point, you assign it a label of 1 and give it to a supervised learner, which I'm calling a learn here, and then you assign it a label 0 and give it to the supervised learner again. Now if both the learners give you, if in both the cases you get back an answer, then you query for that particular instance because the learners did not agree. However, if only one of the learners only one of the cases gives you back an answer, then you simply set the label of that instance to the answer that you got back, and you add this new instance label pair to your set S, which is the set of all the points you've seen so far, and then you keep on repeating this process. This is the solution. The second problem that we have is that of label complexity. That again has been solved for this CAL method. It was solved by Steve Haneke, who said that the label complexity for the CAL method can be captured by the BC dimension D of the hypothesis and by a parameter theta called the displacement coefficient. So for regular supervised learning, in the separable case, the number of labeled instances that you require is D by epsilon, while for a CAL active learner separable case, you require only this theta times D times log of 1 by epsilon. So you see that how you got an exponential increase with an active learner. So the bound is better than the supervised learning, and that's pretty cool, right? And that's in fact why you use active learning. Since I don't have too much time, I'm just going to go on to the applications now. The applications, so this is something that I've already discussed, like why you use active learning. Because so whenever you have a problem setting where you need to train a classifier, you have a lot of training data, but most of it is unlabeled, and you don't really want to or you can't afford to spend too much on querying on an oracle annotating all the unlabeled data. Then you want to query for only some of those data and you want to query intelligently. You don't want to give it because random querying doesn't really help. So that's where your active learning setting comes in. Now it has widespread applications. It is used in computer vision, natural language processing, speech, so on and so forth. I'm just going to take a few examples. One is in drug design. A lot of experiments have been carried out. In drug design especially, you can't really afford to query all the unlabeled instances. If you think that a particular compound does something, you can't just go ahead and conduct experiments on all the compounds, because it's the entire experimental setup is difficult. That gives you the label is difficult, and it's also expensive. So you again want to query intelligently and perform it only for perform the query only for certain number of unlabeled instances. This has been used in pedestrian recognition systems. Then there is the pretty cool open source software called Dualist by Burr Settles. Also, this has been used in sentiment analysis of blogs and many other examples. I'm pretty sure these are just some I came across. And that's it. I hope you enjoyed the video. Thank you.